Hello and welcome to Oxford Philosophy of Physics. It's a great pleasure for me to introduce today one of our own, Nick. Was a product of the Physics and Philosophy undergraduate degree at Oxford and has been a frequent visitor ever since. So Nick, it's lovely to have you here. Nick went on from Oxford to study at Rutgers under the great late departed Bob Weingard, and then after one or two other places is at the University of Illinois at Chicago. And Nick, you're here. I think this, perhaps it's Tushar's influence. You have a pun in your title and a lovely one, missing the point in non-commutative field theory. Nick, the floor is yours.
Thank you, Simon. Thanks for having me. It's great to be here. I think fault rather than influence is probably the right word for the pun, but yeah, it is. So I'm very happy to be here. So I am going to talk through some joint work. Tushar was a bit modest in what he said, if people were around before we started. It's a joint paper with Fedele Lizzi, who's also here today, and Tushar Menon. And there's a longer paper from which this is drawn, and we kind of all contributed to, I mean, we wrote it together, but sort of each of us did more on different parts. Fedele is a mathematical physicist, and so he contributed some of the physics parts, and Tushar and I some of the philosophical parts. And I believe Tushar is going to be talking about some of his parts later this this term or later this year. So you'll get to hear a bit more about of that as well. So I'm glad you pointed out that it's a pun. I do like the pun actually, but sometimes it does confuse people. We're not saying anyone's missed the point. We're going to be clarifying a claim that's been made in the past, that in non-commutative geometry, space does not have points. And we want to kind of make clear, sort of explain what that actually means. So, okay, very good. So the strategy is I'm going to first talk about some classical space. So the things I'm going to talk about are going to seem, are going to be rather trivial to start with, but the point is that non-commutative geometry is a deformation of commutative classical ordinary geometry. So we want to set up the ideas in that context first. And the first thing I'm going to say is in fact very trivial, namely that in classical space, the coordinates will commute. And I see my method of making these slides so that I could appear in front of them has messed up something. There is, of course, supposed to be a square bracket. This is supposed to be a commutator that I have written here. It really is there in my slides. It's the way Zoom's presenting it, but I'll go ahead. Okay, so the coordinates obviously commute. So that doesn't seem like a very interesting fact until you reflect on the mathematical fact that classical geometry can in fact be encoded into an algebra of fields. So in the first place, they have polynomials in X and Y, but other functions that then, other continuous functions form an algebra, and that algebra contains information about the topology and differential structure of the manifold. So when we go to non-commutative geometry, we're going to take that sort of algebraic approach over. I'm not going to talk a whole lot of really much about that, but that is kind of a key idea that's in the background here. And I think Tushar may talk a bit more about that in his talk as well. But all the same, so to make the question of points meaningful, we're going to approach it through the question essentially of particle localization, the question of whether to what scale, how small can you make a particle or identify a particle's location? Does it make sense to think of a particle located at a point? So there's going to be a sort of operationalist thread running through what we're going to say. So a key idea here is that if I ever perform any measurement on a particle for its location, inherent in that measurement is going to be some finite limitation on how accurately I can localize the particle. So for any particular measurement, there's always going to be some ignorance of where the particle is, a measurement of particle location, and that's naturally going to be represented by an epistemic state, which is sort of natural to take as a Gaussian. Okay, so here's the state I would use to represent, after I've measured a particle, to represent the position of a particle. I know it's somewhere basically with it, it's somewhere around x0 with a kind of Gaussian width of alpha. Okay, for this slide, I'm going to work in one dimension just to kind of keep the equations as simple as possible. And you'll see when we go to non-commutative geometry, we'll have to be we'll work in at least 2 dimensions. So we'll be working in the plane, but that'll be fine. So, but although we've just acknowledged that any particular measurement has a sort of practical physical limitation on how well it can localize a particle, points are still, there's no sort of, in principle, lower bound on how good a measurement we can perform. That measurement, one measurement has some lower bound, but I can always, in principle, find a better measurement that will localize particles even more. And there seems to be, and classically, there's no limitation on how well I can localize a particle, how good a measurement is possible. And so there's no lower bound on alpha. And so although no position, no individual measurement will localize a particle to a point, the point is just the limit of the what measurements can in principle be performed. So in that sense, points are fine in classical commutative geometry. Okay, and just to remind you of sort of some of the, oh my Lord, okay, the framework. Okay, sorry, can I just pause? I'm going to just use my regular slides. This is not working. I'm sorry. This is going to be a mess. So I'm just going to stop sharing and start over. Okay. Okay, well, I blame David for this. I was very impressed by the lecture he gave in the corner, and I thought I could manage to do it as well, but clearly not. Let's see. All right, so we'll do it this way, and you'll just have to look at me in my office instead of, imagine I'm sitting in the corner. You can probably drag the little picture of me to the corner if you like. So, well, just another way in which my lectures don't live up to, only kind of aim to be as good as yours, David. Okay, so to go back. So, okay, so given this epistemic state representing, the position of the particle, of course, we can introduce, just classically, expectation values for various quantities. So, for instance, the expectation value of position naturally is going to be where the Gaussian is centered, and I also give the expectation value for x squared. From those, we can compute the uncertainty, which is going to be alpha over root 2. And of course, as we're kind of emphasizing, this uncertainty is just sort of ignorance as a result of the measurement. So I hope there's nothing kind of new or sort of surprising that's here. It's all set up so that we can import these same ideas into the non-commutative context, where things are going to look rather different. But as I said, there's no limit on how good and what measurements are in principle available to us. And so as you became increasingly certain about the localization of a particle, the limit, we can take alpha goes to 0. We can make the Gaussian as narrow as we want. The uncertainty can be as small as you want. And in that sense, point localization makes perfect sense, even though we don't admit, a measurement that tells us, any particular measurement that tells us exactly where a particle is. But the point is going to be, in non-commutative geometry, this story is going to fail. And we're going to show two ways and explain two ways in which this picture breaks down in non-commutative geometries. Okay, so first of all, sort of a slide just telling you about what a non-commutative space is. Excuse me. So in this talk, I'm going to refer to a very sort of toy theory of non-commutative geometry. So basically the simplest kind of case that you can imagine to just illustrate the point of non-commutative physics, non-commutative field theories. You know, what's really in the background is some more realistic physics, such as Alan Kahn's the spectral triples physics. But the points about points are more clearly made, the ones I want to make today are more clearly made in this simpler context. But what we're saying still applies to sort of more realistic physics. And I believe, yeah, Tushar will be talking about the spectral triples idea. Oh, damn it, sorry. All right. My apologies. Okay. So the basic idea of the non-commutative space is going to be taking that trivial commutation relation, the coordinates x and y commute, and impose a non-commutation relation on them. They're not going to commute anymore. So xy is not going to equal yx anymore. Okay, so how are we supposed to? What are we supposed to do from there? Well, I'll build that up a little bit, but in the, we can carry on constructing an algebra in the way I sort of suggested before. For instance, taking polynomials now in this non-commuting x and y. Okay, but I'm going to multiply them on the assumption that that x times y minus y times x is equal to I theta. So I'm not going to be able to assume that I have a commutative product anymore in my polynomials. But I can still build up all the polynomials, and they'll all be defined, and they'll have an algebra between them in virtue of this algebra between the base elements. And so I can think of those elements of the algebra, those polynomials, and then they can be extended to non-polynomial functions. Okay, infinite and finite polynomials. They're going to form an algebra in virtue of this base algebra, in analogy to the way point-valued commuting fields do in commutative space-time. And once again, the goal of the game is going to be to extract geometric information from this algebra. And the sort of important thing is most of the things that work in the commutative algebra will still work in the non-commutative algebra. Okay. So that's, again, kind of going on in the background. I'm just going to extract some of the results of that, but that is sort of the basic idea of what's going to be going on here. Okay, well, because we have this non-trivial commutation relation, well, we're going to still be talking about space via this algebra, but in an algebraic way. The space we're talking about, we're going to sometimes call quantum space. You might want to call it non-commutative space, and there's sort of divergence in the literature about whether to call it quantum space or not, but I just want to take a little aside to kind of clarify what's going on here. So in the first place, the name quantum is justified purely by this non-trivial commutation relation between the coordinates. So, but just to sort of be clear here, I haven't said anything about h bar here. This is theta, not h bar. Theta could be equal to h bar, but we're not assuming that. So the physics I'm talking about is not quantum in that sense, or not yet. But maybe more importantly, one can define an action in terms of these non-commutative fields. I mean, just as one can write down an action in terms of commutative fields in the classical case, one can still write down an action in terms of these non-commutative fields. And indeed, much of classical physics will still apply to it. But that means we have a choice. Once we have the action, one can either apply sort of Hamilton's least action principle to the action, in which case one has sort of classical physics in quantum space-time in the sense we're talking about. And that's the kind of physics I have in mind for the first part of the talk. But one could also apply Feynman's path integral principle to the action. And then one would have quantum field theory in quantum space-time. Okay? But classical field theory in quantum space-time, the way we're using these terms is also on the table. And at the end, we will appeal to quantum field theory in quantum space-time. If you talk about it for a while, you'll find non-commutative space becomes quite a mouthful. So it's actually quite nice to just be able to say quantum space to mean that instead. But please understand this caveat that it's not quantum mechanics. The matter in the space-time is not quantum mechanical in the sense of applying following a path integral principle. So we mentioned this, well, just to be clear. So, and also to emphasize that amongst physicists, the use of whether people are prepared to call this quantum space or not is mixed, and indeed people sort of disagree about it. But there is a pedagogical advantage to our doing so, which is that it just tells you, well, look, lots of the things you know about quantum mechanics are just going to carry over into, will apply to non-commutative space-time. So basically, what you know about the quantum formalism is going to apply. What you get from quantizing position and momentum, the mathematical formalism that comes from that is going to be the same formalism, or largely the same formalism that you'll have in mind now where we have a commutation relation between the coordinates x and y. Moreover, we're going to just use this to appeal to parts of the sort of standard interpretation of quantum mechanics. Okay, so if you sort of think about having quantum mechanics in the back of your mind, that will help you sort of, I think, follow more quickly what's going through with what we're talking about here. So in particular, in quantum mechanics, so if we're posing a commutation relation between x and p, we now have to have a map from classical functions of x and p into operators. Functions become operators. And so that's also going to be the case for non-commutative space. And we're going to need a quantization and dequantization maps between classical functions and non-commutative operators. So for instance, we're going to be relying on what we talk about on the Weil map. So if I have, I don't know, can you see the cursor when I move it? Yeah, okay, good. So if I have a space-time function f of xy, then I have this Weil map, which will give me an operator, which basically says take the Fourier transform of f of that function, and then sort of do an inverse Fourier transform, except instead in my harmonic term, I'm going to put in operators instead of functions x, y, and that'll obviously give me an operator. And there's an inverse map that we can take as well, which involves taking the trace to get back to the Fourier transform of my space function, of my non-quantum function. Okay, so on the left we have non-quantum, on the right we have quantum. Okay, I'm going to apologize a little bit at this point, or to maybe half the audience, for some of the use of equations here. I've put in more equations, or some equations that I don't strictly need or that I don't plan to talk about in depth. That's because A, they're there in the slides, the handout of the slides, for anyone who wants to look at them later and refer to them later and think about them. But also, I suspect there are people in the audience who also are familiar with this framework, and I want to make clear to them just how what we're saying sort of fits in with what they know. That is one thing I didn't say. If you go to the chat, I actually put in a link where you can download a PDF of the slides if you want to have that while we're talking. I think it should still be there. Okay, the important point though is we have a map from, a quantization map that'll take us from classical functions to quantum operators, and that's what we're going to be leaning on in this next part of the discussion. So I'm going to just repeat what I said earlier, is that familiar dynamical principles will still apply. So I can just write down an action in terms of the elements of the algebra, and it turns out, say, Hamilton's least action principle will work. The important thing here is that the derivation of Euler-Lagrange equations only depends on associativity, not commutativity of the field. So you can still apply sort of ideas of Euler-Lagrange equations and least action to get dynamical equations out, which is pretty interesting and surprising. Okay, so we've made this huge change to space, but in many ways, physics looks pretty similar. You just have to be prepared to work in algebraic form rather than a non-algebraic, rather than in terms of real analysis, although we'll come back to that again in a minute. And maybe it's worth mentioning one other case situation in which you might have kind of come across the sort of ideas of algebraic spacetime is in the idea of an Einstein algebra discussed by Garrosh and discussed by Ehrman. That's classical, but that is what they're talking about there is, again, the idea of an algebraic formulation of general relativity. Okay, so that's something other people might have known. Okay, so we've looked at particle position in commutative space, where things look pretty trivial. I've now given you a short introduction to what a non-commutative space is. And now I want to sort of put those two together and essentially quantize the discussion from the first slide. So, okay, so we take our classical epistemic particle state, apply the quantization prescription to it, and this is the operator that comes out. Okay, and here I have to thank, we see here definitely the contributions of Fedele and his students. But this is what the quantization looks like. So a couple of comments. This is two-dimensional now. Of course, we're going to have to work in 2 dimensions, otherwise we won't see the non-commutation between x and y. And this is just the result of the prescription, the Weil map that I mentioned before. So this is an operator. One can now give a Hilbert space representation of this operator formalism of the algebra and work out what it actually what this looks like as and then in that framework give a matrix representation, and the matrix representing this density operator has been worked out, and this is it. Okay, so obviously there's a fair amount going on between the classical epistemic state and this matrix, but again, I'm just going to appeal to your understanding of quantum mechanics to say we first quantize and then find a Hilbert space matrix representation, find a basis in which the density matrix, the density operator diagonalizes, and I'm just going to quote, this is the solution. Okay, so this in a particular basis is the quantized version of that epistemic Gaussian state that we started with, representing our ignorance in the classical case. A couple of citations there to where you can find this, one on the archive, maybe a special shout out to Lorenzo Leone, who wrote this as his undergraduate honors thesis for Fedele, working this out. Okay, so what does this matrix show? Okay, well, to get to that, we want to state a principle for interpretation here and import some of the standard quantum ideas. And according to standard quantum ideas, if I have a density matrix and I diagonalize it, those diagonal elements better represent, or at least be capable of representing probabilities for finding the states corresponding to those to the eigenstates of that basis, or the basis states. Okay, I'll also note that these states, if we're interpreting things quantum mechanically, these numbers are going to be ontic probabilities rather than epistemic probabilities. So obviously the question of probability in quantum mechanics is vexed, or at least vexed for some, or controversial. But I think you can more or less fill in whatever interpretation of ontic probabilities you like for quantum mechanics. But the important point is, in quantum mechanics, if I diagonalize my density matrix, density operator, then what I'm finding on the diagonal are probabilities. And so that the object I've written down can only be physical if the diagonal elements are all positive numbers. Okay, and we're calling this principle state physicality. Okay, it's a requirement on rho actually being a physical state representing some physically possible system, that these diagonal elements all be greater than 0. Okay, so clearly whether those numbers are greater than, are positive is going to depend on the values of alpha and theta. Okay, so let's look at that. So again, we're looking for these elements to be positive, and there's the matrix. And there are clearly 3 cases that we need to consider. So here's the first one. First case we might have is that alpha is greater than square root of theta. Let's just pause for a second to make sure we're remembering what alpha and theta actually are. So alpha is the radius. So we're talking about this is the quantization of a 2-dimensional Gaussian. So it's a Gaussian in x and y. Alpha is the width of that Gaussian. So that's kind of a measure of how localized the particle is. Theta is the commutation parameter, right? The commutator of x and y is now taken to be theta, right? Clearly that's proportional, that has the same units as x times y, so it's an area. So the square root of theta is also a length. It's kind of the smallest, it's the length associated with the non-commutation parameter, which is itself an area. So this is the case in which the Gaussian is wider than this non-commutation length. Okay, and then clearly things are all okay. The particle's not localized within this radius square root of theta, but all the diagonal elements are greater than 0, so this is a physical state. So no problem quantizing states where the particle is spread over more than a size greater than theta. If you want to think about, its area, as it were, is it's greater than theta. The next case, of course, is where alpha is equal to theta, and you can see quite easily that I'm going to get 1 in the top in the first element, and all the others are going to disappear. So this is basically kind of a pure state where the Gaussian is localized exactly at the area of in which the particle is localized is basically the commutation area. Okay. But then the case we're interested in, because we're thinking about particle, is there a lower bound on particle localization, is this third case, where we take a classical state that's localized within the commutation, the sort of commutation scale, square root of theta. Well, now we get that the first element is greater than 1, but in particular, we're going to find elements down the diagonal that become negative. Quite clearly, the 2,2 element is going to be negative. And so we see, if you try to quantize a state that is, where the particle is localized below this theta scale, then you end up with an unphysical operator. You don't end up with a quantum non-commuting state for the system. So in this sense, there's just a failure of there to be states where particles are localized below a certain scale, below the commutation scale, because of the non-commutation. Okay, so just to sort of recap, the epistemic state in classical space can be localized arbitrarily, but if you try to quantize states that are localized arbitrarily, in quantum space, the corresponding ontic state is unphysical if it's localized within the commutation scale, which is to say, states in quantum space cannot be arbitrarily localized. And then, so that's the first sense in which there are no points in non-commutative space, in quantum space. There's just a lower limit on how small how finely particles can be localized. So insofar as we're, probing the idea of localization and points and small areas in terms of where particles can be localized, which is what we're assuming, there are no what this is saying is that there are no regions smaller than theta, and in particular, no points. Okay, so that's the first way we come to the conclusion that non-commutative space is pointless, that the points are missing. I'm going to give another discussion, which is a sort of different way of coming at the same point, which has a little more sort of operational flavor to it. I mean, I guess the first part does as well when you're thinking about the possibility of localizing particles. So, but I'm going to give a different sort of approach, which will also set up a another kind of machinery for approaching non-commutative geometry. This second way of thinking about things is completely compatible with the first, but I think it'll give you a different kind of insight into what's actually going on. So first, I'm going to set up this new framework, and that's the sort of natural idea of saying, look, I have this algebra. What's the natural way of kind of representing that algebra? Well, a natural thing to do is to take some differentiable manifold and take just ordinary point valued fields on that manifold, so functions over the manifold. And now how am I going to get my non-trivial commutation relation? Well, I'm going to have to define a new product. I mean, the dot product commutes, right? That's just a product of the, that's just a feature of the dot product. But maybe we can introduce a new product, and so a new commutation relation. So it's going to be square bracket star, which is going to be x star y minus y star x. For any functions I put in there, it's going to look like that. And I'm going to define my star product so that it has this feature: x star y minus y star x is not equal to 0, but to I theta. And well, here's one that will do it for you. Again, apologies, I'm not going to stop and talk about this at great length, but clearly the feature of the star product is that it has the dot product plus a correction term, which of course has theta in it. And this is the Grunewald-Moyal, or just Moyal star product. I guess like the BBC, I should note at this point that other products are available, but this is the one that we're going to talk about. Okay, so now, we're just going to use this product to represent the rest of the algebra. The function x, which of course is a function on the manifold, and the function y, right? Coordinates are functions, they are fields on the manifold. Now, of course, one can now generate other elements of the algebra using the star product. So any polynomial element of the algebra, finite or infinite polynomial, can now be generated just by star producting x and y, the requisite number of times. Okay, so I can take, here's an example: ax times b x star y plus c y star x star y. Okay, and that gives me a field. And so this gives another sense in which the elements of the algebra are fields, but they can be represented by actual functions over a manifold. Okay, so one would still be able to now do field theory with these objects, say writing an action down. But all you would do is sort of quantize. The natural thing to do would be, you never get to use the dot product. You're always going to put in the star product. I guess you can put the dot product in if you want, but you're going to use star products instead of dot products in your action and in your physics. And then you can now sort of apply real analysis. So there's, in a sense, the standard techniques of mathematics are available to you. It's just if you had a scalar field where everything was kind of nice because you had a dot product, you're always going to have all these extra terms and things are going to be sort of messy. But the mathematical framework of analysis is now going to be available to you in this representation. And indeed, if you actually want to calculate some physical quantity in non-commutative field theory, a scattering amplitude, say, this is the approach you would take. you'd use this framework because you can actually, compute integrals and and so on. Good. So just for a reminder, just to emphasize the key point here is that this star product, of course, is to be carefully distinguished from the dot product, which does commute, which is commutative. Okay, so here's some sort of discussion, sort of thought that may have kind of occurred to you now relative to what I've just what I said before. Well, look, we started with the algebra, a non-commutative algebra of fields, and it's pretty clear there's nothing sort of explicit, there's no explicit manifold there, so it's not maybe so surprising that there are no points. But what's going on now? This Weyl representation, we have point valued fields living in a point manifold and coordinates that certainly commute according to the dot product. So maybe all that stuff I said earlier was just kind of misleading or confused in some way, because here's how we should think about things. If I have a non-commutative field theory, a non-commutative geometry, look, really it lives in a perfectly ordinary differentiable manifold with points and arbitrarily small areas. It's just that the physics, say the action, uses the star product rather than the dot product. Okay, so there's what the physics, and that's really what's going on in the situations that I'm talking about. But that's not really going to wash. As soon as you say, or at least from the point of view that we're thinking about here, as soon as you say, look, the physics only cares about the star product, then you are fully committed to the state space we were talking about. And so that there's no localization of particles. It's also going to apply to what measurements you can perform. I'm going to give sort of an example of that. That if the physics only cares about the star products, then there's not going to be any physically meaningful measurement of a part of location below the theta scale. So to adopt that view that really space is pointy, really a continuous differentiable manifold, you have to be kind of decoupling reality from physics in a profound way. And so we're going to be appealing to this, sort of a kind of tempered operationalism that I'll talk about later, where what's actually relevant and what we're interested in is, what is there physically speaking? And from that point of view, it doesn't make sense to try to add to the physics, the physical theory we have, some further, invisible, physically OTO structure, the differentiable manifold with points. And so instead, one should think of the Weyl manifold not as representing, a real space in which the world occurs, but really it is just a representational device. And that's the sort of attitude people usually have to this, where these fields, these Weyl fields that I've been talking about, they're just representation, they're just, a way of a concrete representation of the algebra, sort of in the familiar sense. And indeed, they're not thought of as sort of fields extended in space, and they're often referred to as symbols for that reason, just to emphasize that. Okay, so put that to one side, but maybe something people want to talk about. But once we can now sort of see something more operational about, you can sort of imagine what's actually going to happen if one tries to, in fact, measure position below the theta scale. So we sort of saw before that there can't be states where a particle is localized below theta. Now we want to there's a sort of flip side to that. So that's like a sort of a kind of preparation side of things. Could I prepare a state? Well, there aren't any such states. What if I tried to measure something locally, then at a smaller scale? So first, let's think about what a classical position measurement actually looks like, and then we'll do the same thing as before and quantize. Okay, so the kind of measurement we're going to think about is sort of a yes-no measurement of position. Okay, basically we're going to ask, is the particle at x lambda. Okay, so but as before, we're going to use a detector that has limited accuracy. Then the natural observable to use is this one. So again, the detector is going to be represented by a Gaussian that is representing our sort of uncertainty. And if it says in its answer yes, if it says yes, how certain are we about that? You can think of it that way. So I'm going to we're thinking we've got our Gaussian state with uncertainty alpha. We've got our measurement device with uncertainty parameterized by beta. For simplicity, just set them equal. And then the expectation value for this operator in our epistemic Gaussian, okay, we're working classically, is going to be this Gaussian, which of course depends on the difference between where the particle is, or where the Gaussian of the particle is centered, and where the detector is, or where its Gaussian is centered. Okay, so that's the expectation value. Again, I emphasize all classically. So, but the key thing is, if I bring the particle and the detector, the closer I bring the particle and detector together, of course, the greater this quantity is. And as the distance goes to 0, this goes to 1, and so that's why we have the normalization we do. That's kind of what we want. We want to think of this expectation value as the probability that the detector will say yes. And if the detector is right on top of the particle, then it's bound to say yes. Okay. What happens if we move the detector away from the particle? So theta has no, we're talking classically, so theta has no actual significance in what we're saying. But this is the case I'm going to consider on the next slide in the non-commutative case. So let's just say we have two particles that were localized to 1/10 of the non-commutation scale, and that then they're going to be placed 5 times that distance apart. So their Gaussians are hardly overlapping at all. Okay, so they're 5 times further apart than they are wide. And then of course the expectation value is going to be really tiny, a really tiny number. Okay. So of course what we want to think about now is that all makes perfect sense in the classical case. What if we introduce the non-commutation, the non-commutation parameter? We have theta, and now x and y don't commute. And we'll again try to perform these measurements. So again, we're going to start with classical Gaussians, one for the localized particle and one for the position measurement. But then now we're going to be working in the Weyl representation and using the star product to make it for our calculations instead of the dot product. So I should say, in the Weyl representation, the operators, rho and lambda, will also be Gaussians. The Weyl representation will take those Gaussians into Gaussians as well. They will actually be Gaussians, but when we calculate quantities, we're going to use the star product. So let's work through the same case, see what happens. So once again, we're going to take the width of the particle Gaussian. We're going to try to set that to 0.1 square root of theta. So, I mean, we've already seen this shouldn't work, right? Because there is no such state. I can't have there isn't a physically significant state that has this characteristic that where a particle's localized behind to 0.1 of the non-commutation scale. I can still write the Gaussian down. The point is it's not going to represent a physical state. And what we're going to see is the result of that. Similarly for beta. So we saw classically that lambda times rho, I mean, we took the expectation value, but we're going to integrate that. But basically this is 0 everywhere. So we're going to get, the integral is going to be 0. That's really what we saw before, or very small. But Okay, not surprisingly, because in the classical case, because I'm multiplying two Gaussians that are 5 times further apart than they are wide, so it's basically 0 everywhere. But if I take the star product, things look very different. Okay, and here's two nice graphs that Fedele prepared to sort of talk about to make the point. So let me talk through what's going on here. So the first thing you need to know to realize is that the star product of these two things is not a real number at all. It's a complex number. So we've broken it up into the real and imaginary parts. So that's a difference. The units are along the bottom. So the vertical scale is, of course, just what the product is equal to. The units along the bottom are in terms of Gaussian widths. So each one is equal to 0.1, 1/10 of square root of theta. Okay, so 20 is twice, so 20 here, units here would be 2 times theta, which is the 20 Gaussian widths. And where I have two Gaussians, they can only be separated in a line, and that line is the axis that's sort of in the front, the one that's running more left to right rather than into the page. That's why you see the asymmetry in these diagrams. Okay, so don't worry too much about the axis running into the page, but the one kind of across the page, that's the what this product is equal to along the line connecting the two, the particle and the apparatus, I should say. And of course, what you see is it's not equal to 0 at all. It's equal to a small value, but it's non-zero. And in particular, say, look around, here, so about 10 Gaussian widths from the location of the particle, 10 Gaussian widths from the location of the particle over here. And you can see I'm still getting non-zero values of this product, even that far away, which is to say, even though these are separated by 5 times the Gaussian width, the apparatus is still seeing the particle. Even at a point 10 times, 10 times further away from the particle than its Gaussian width, the detector is still seeing it. That point is also twice as far as the separation between the particle and the detector. So there's at this scale, because we're trying to do what we're seeing is because we're trying to have particles and particles smaller than the non-commutation width, and detectors smaller than that are more sensitive than the non-commutation width. This massive non-locality that's built into the star product that sort of occurs inside these scales is messing things up. This is no way doing anything like localizing. As I said, of course, this was kind of nonsense in the first place, because we've already seen there can't be any physically significant states that have this character, have a Gaussian width of 0.1 theta. Theta, square root of theta, is the smallest width they can have and still be physical. Okay, but this helps you sort of see what goes wrong if you try to treat such a function, such an operator as a state. It doesn't make any sense. We're not, the apparatus is no longer doing a particle position measurement. And so this helps illustrate how sort of an observation of scales smaller than the commutation length breaks down, doesn't make physical sense in this theory. Okay, that's what I said. The detector can see the particle way beyond the region in which the state and the measurement are supposedly located. It's also the case that if you take this expectation value, which is supposed to be the probability of the apparatus, say yes, you get an imaginary number. So that also doesn't really make any sense. Okay, so when I say position operationalize, I've kind of in the background thought about how one would operationalize a position measurement, but the point is that operationalization does not work once you go below the commutation scale. Okay, just time check. Very good. So let me just review what we've shown, and then I want to sort of talk a bit about some of the consequences. So, okay, I've told you what a non-commutative or quantum space is to some extent. The first result showed that if we have states supposedly representing localization within the commutation scale, they will turn out to be unphysical. They will have negative probabilities. We've just seen if you try to describe a measurement that will localize a system within the commutation scale, things go crazy. You end up with non-physical results. I mean, not surprising given the first point. So what we conclude from this is, so given some standard assumptions about quantum probability, namely what things actually represent probabilities in quantum mechanics, and a mild tempered operationalism. So let me just talk a bit about that for a moment. So we're not suggesting an operationalism where a physical quantity has to be defined by the operations that measure it. And thinking of philosophy of physics, I remember Rom Hare sort of trying to beat that as an attractive idea out of me long ago. But we do say that a physical quantity has to be measurable somehow. It has to make some difference to some physical process. And so in that sense, we'll be sort of milder tempered operationalists. And that's what's really failing in these kinds of cases, in that we can't measure it. I mean, there's no way to measure locations, particle locations below the commutation scale. So there's a failure of an important and I think generally accepted kind of operationalism. So given those two premises, then regions smaller than the commutation scale, a fortiori points, are unphysical. And so, well, if there's no points or localized regions below a scale, it must be the case that these apparent non-commutative field theories are really not theories of pointwise spatial fields at all. Good. Well, that raises obviously some pretty significant questions. The first kind is, what actually is the ontology of this theory? What kind of theory are we talking about here? Well, the most natural formulation is that it's an algebra. This theory is formulated fundamentally what it's about is not extended objects in space-time, but it's a theory of an algebra. Those are the basic things. And somehow they shouldn't, you don't want to, those elements of the algebra don't have to be interpreted in terms of fields in space-time, but somehow what they do in the theory, by their role in the theory, in the dynamics and in the rest of the kinematics, the rest of the theory. But what kind of ontology is that? So one kind of thought here is to just sort of bulk at the idea that there could be things that aren't spatio-temporal, but such things perhaps aren't even comprehensible. So one thing we argue in the paper is that really comprehensibility doesn't require visualizability. Excuse me. So if your objection is I can't kind of picture this, then that's really no sort of objection at all. And if you buy that, then one has to move on to sort of think about what should one understand such a theory. And then we have some discussion of some options you might want to sort of try there. So you might try a kind of algebraic substantivalism about the elements of the algebra. You might try kind of anti-substantivalism about them that we sketch. And in the discussion of Einstein algebras, there's some discussion of interpretation there, which is sort of relevant here. And in particular, Jonathan Bay sort of suggests a kind of structuralism about elements of Einstein algebras that might work here. Okay, those aren't the questions I wanted to talk about. There is one more question in the last few minutes that I want to just run through. And that's the question of where do, if the fundamental ontology, the fundamental theory is an algebraic theory, how so do we end up with the local space-time physics that we do? So I guess I'll ask the question the way I've written it here. So what we've really seen is there's no so we're going to come at things from the point of view of the Weyl representation. And what we've really established is point values of those fields sort of don't have physical significance. What really has physical significance is the whole element, the whole function, okay, the whole configuration over space, which is representing an element of an algebra. How can one go from, in that picture then, whole field configurations? There's physical significance to a field, you know, in the sense of a function, you know, what function it is over the whole of space, but not on its values at particular points. How do we go from sort of whole functions, complete configurations, to the localish space-time measurements that we rely on, we make and all the time and rely on? And so this is the question of the emergence of space. I don't mean emergence in a very heavy sense here, but in a sense that many people talk about it these days. I mean, it's compatible with reduction, but what it involves is stable novelty, I think is what's new. Okay, and I would say space, you know, a commutative geometry is novel relative to a non-commutative one, hence justifying the use of the term. Okay, so I apologize if this goes a little quickly, but let me just run through this. So we're going to work in the Weyl representation. So we take elements of the algebra and represent them by fields on a differentiable manifold. But again, it's a representation. As I said, we're going to now work on use quantum field theory in quantum spacetime. So not Hamilton's principle, but Feynman's principle. And I'm going to focus on, because I'm in quantum field theory, 2-point functions. These are kind of nice to think about. These are the sort of point-to-point correlation functions in quantum field theory. These are nice to think about because they lead, you know, because scattering amplitudes, scattering cross sections are can be defined in terms of them, and scattering cross sections seem to be nice empirical spatiotemporal entities, you know, objects that one can think about. They describe the relations of incoming and outgoing particles. They give you information about the angles between them. They are nice localized space-time events. And so if one can recover scattering amplitudes, scattering cross sections, I think that's how people often understand what it takes to kind of be recovering space-time from some non-spatiotemporal theory. And so we'll focus on the 2-point functions from which they can be derived. This is just the sort of standard quantum field theoretic account of what a 2-point function is. You know, it's the vacuum expectation value of a product of the operators, and in the path integral formulation will be obtained by a path integral over that product weighted by the usual sort of Feynman path, you know, integral weight, which you know contains the action, the I, e to the I times the action. Whoa, excuse me. I think the point I want to make is, you know, what I've been hammering away at for a long time now is that these Weyl symbols are not fields with respect to physical space at all. They just represent elements of the algebra. And so they are sometimes called, as I said, symbols. These 2-point functions can't be understood as functions over space-time either. They're just symbols. They're just sort of something definable in the algebra. So the question is, where do we get space-time? How do we get space-time back? And I'm going to make a brief proposal for recovering commutative space. I think I want to say, I kind of like this proposal, but I'm not particularly wedded to it if somebody has a better proposal. The reason for giving it to you is sort of twofold. One, to show how it could be done, a sort of proof of concept of deriving commutative spacetime from non-commutative spacetime, but also to make just a point about what it takes for emergence of spacetime. So just because the Weyl fields don't have meaning in terms of localized quantities, it doesn't follow that other objects defined in terms of them don't either. So here's a formal procedure actually for defining a new set of objects. Okay, and this comes from just a smearing operation that comes from some work by Chaichian, Demichev, and Presnida, CDP. And it says, give me a Weyl function. I'm now going to you can see what's going on here. I'm going to define a new function, phi p. And if I want to know the value of phi p at x, I'm basically going to smear the Weyl field around x. I'm going to use a Gaussian. So basically, phi p at x is containing information about the value of phi of the Weyl field smeared all around the region x. Okay, there's a motivation for taking this that you can ask me about. But for our purposes, smearing seems to be about the right thing to do here, to go from non-commutative to commutative physics, because exactly what's wrong with exactly what's at issue with the non-commutative space-time is there's no information below a certain scale. So what this does is smear across that scale. So because we don't care what the information actually is. So we fully expect, even if the Weyl field, phi w, was physically meaningful at all scales, we would expect phi p only to be meaningful above the theta scale. So this is a nice kind of operation. So CDP invoke this, in fact, because they're worried about renormalization. We're proposing to use it in a different way through the following ansatz. So looking at this equation, the x prime that we're at, one integrates over, is just the just represents the coordinates on the Weyl manifold, which is just a representational device. But we want to interpret x on the left-hand side, the unprimed x, as representing positions in space. So put another way, the phi w have no physical significance in terms of localized quantities, just as an element of the algebra. But what we're postulating in this ansatz is that the phi p do have local physical significance in space. So these things look the same, but really there's two spaces involved. X prime is ranging over this representational space, but we're proposing that the phi p, the x in there, ranges over what we mean by space ordinarily, the space around you. Okay, so now we can use, given this map, we can now define physical two-point functions, and so these would then refer to actual scattering amplitudes that we observe. So this step, we now have effective space-time quantities, the two-point functions and cross-sections. But I do want to emphasize, it's still going to be the case. This is an effective, an effective description of commutative space-time quantities. But that effective description, it's built in that it breaks down below the non-commutation scale. I mean, the phi w's don't break down below that scale, don't have physical significance. And moreover, we've smeared across them. So the sense in which this has space-time significance is in any regions larger than theta. The point is the phi w's don't have any significance in regions smaller than the whole of space-time, because that's how they represent elements of the algebra. And finally, the last slide, and okay, I apologize for going a bit over. Regarding the last discussion, what was key here was the necessity of positing a new interpretational ansatz to connect the non-spatial to the spatial. The thing I labeled as the ansatz, that this move from the Weyl fields to the physical fields, the smearing, takes us from objects in the non-commutative geometry to objects in an effective commutative geometry. Okay, so what we want to suggest is, however you do this, however you explain the emergence of commutative spacetime, you're going to have to postulate something like this, connecting the non-spatial to the spatial. It's going to have to be novel because all the physical interpretational postulates we have are currently spatial. Okay. But that's okay. It's going to have to stand or fall with the data it entails. If this doesn't produce, the correct empirical physics, then it's not any good. If it does, this is a postulate we will come to accept. But as I say, some such postulate is going to be needed. All right, and that's really it. So you can see the paper, and that's me for now. Thank you. And again, apologies for going over a bit there.
Thank you.